Picture this. A virtual character pulling off a gravity-defying double Kong jump, soaring over obstacles. It looks like something a real parkour athlete would do. You can actually see a video of this.
Yeah, it's pretty incredible to watch.
And what's really astonishing is that no one sat there and painstakingly coded every single muscle movement. It learned to do that itself.
Exactly, and that remarkable leap, a virtual character learning these incredibly complex physical skills, that's precisely what we're diving into today on the Deep Dives.
Right.
Think of this as your shortcut, your streamlined guide to some really groundbreaking research. We'll distill the key insights so you don't have to wade through all the dense technical stuff yourself.
Okay, so our mission today is to unpack this fascinating study. It's from Ziyu Zhang and colleagues, published in 2025, and they've tackled a really big challenge. How do you get virtual characters to move with that kind of super realistic athletic motion?
And their answer is this new technique called ADD, which stands for Physics-Based Motion Imitation with Adversarial Differential Discriminators. Quite a mouthful.
It is, yeah. But for you, the learner, this isn't just about, say, cooler video game animations. This research actually tackles a core problem we all face, right? How to effectively manage multiple, sometimes competing priorities.
Absolutely. I mean, think about prepping for a big meeting where you have maybe 3 or 4 different objectives you need to hit. Or when you're trying to get your head around a new subject with lots of different facets, juggling those different goals effectively is key.
For sure. And, the older ways of doing this kind of animation involved a lot of manual effort, like literally someone tweaking virtual knobs to try and get a walk or a jump to look right. Even with reinforcement learning, which was a big step forward, engineers often had to design these really complex reward functions, basically telling the system very precisely what good movement looks like and how to achieve it.
Sounds tedious.
It is. It's very hands-on, often a lot of trial and error, very time-consuming.
And that's really where this new ADD technique comes in. It offers a really elegant solution, actually. It's a way to automate this balancing act between multiple objectives.
So we're going to explore how this adversarial differential discriminator, ADD, works its magic.
Yeah, exactly. What makes it different, what makes it such a step up from previous methods, and why it's a pretty big deal for getting virtual characters to master these incredibly agile, dynamic skills. Okay, let's get into it.
Right. So maybe start with the challenge itself. Why is it so hard to make virtual characters move naturally? We've definitely seen progress. Characters do more than just walk now. They can do some pretty complex stuff.
Well, the traditional approach, especially in reinforcement learning, relied heavily on these reward functions. Like training a dog, you reward it for doing the right thing.
Okay.
But defining the right thing for complex movement is tricky. Engineers had to manually craft these really intricate reward systems, trying to encourage realistic physics, balance, joint movement. It takes a lot of expertise and fine-tuning.
And then came adversarial imitation learning as an alternative.
Right. The idea there was, instead of telling the system what's good, let it learn what looks good by comparing its own attempts to examples of real human motion.
Like having a critic watching?
Kind of, yeah. A system the discriminator learns to tell the difference between the virtual character's movement and the real data. It develops an eye for what looks human.
But there's still a gap, right?
There was.
Yeah.
These earlier adversarial methods were pretty good at capturing the overall style or feel of human motion, like a general walking style. But they often weren't great at precisely replicating a specific motion clip, frame by frame.
Ah, I see.
And for some applications, like, say, medical training simulations or analyzing an athlete's-specific technique, you really need that precise replication. Style isn't enough.
Okay, so that brings us to this paper's approach. Adversarial Multi-Objective Optimization, or MOO, which is the core of ADD. Multi-objective. Let's break that down. What does it mean here?
It just means you have several goals you're trying to achieve all at once. Think about that backflip again. The character needs to push off correctly, rotate the right amount, keep its balance, spot the landing. Those are all different objectives. For the backflip to look good and be physically plausible, the system needs to optimize all of them simultaneously.
Right, like a gymnast hitting every part of the routine. So the old way was loss balancing, which sounds like just adding up all the errors.
It's a basic idea, yeah. You calculate an error or loss for each objective, how far off was the rotation, how unstable was the landing, etc. Then you typically assign a weight to each error based on how important you think it is.
Okay.
Then you add up all those weighted errors into one big score, and the system tries to minimize that score.
But the problem is choosing those weights.
Exactly. That's the killer part. Figuring out the right weights is really hard and often involves endless tweaking. Get the weights wrong, and maybe your character does a perfect rotation but then face plants on the landing because balance wasn't weighted enough.
Okay, so ADD and its adversarial differential discriminator is trying to bypass that whole weight guessing game. How does it work?
So the key idea is using a learned component, the discriminator, to automatically figure out the best way to balance these objectives, instead of manual weights.
How?
It looks at something called a differential vector. Think of it like a detailed error report. For each objective rotation, balance, position, velocity, this vector shows how far the character currently is from the ideal performance.
So like a list of errors for each goal, negative 10 degrees rotation error, 0.5 meters position error, etc.
Precisely. Now, the discriminator's job is to look at this whole vector, this whole error report, and learn to judge. Does this report represent a perfect performance? Meaning, are all the errors zero?
Okay.
And here's the really clever bit, the core insight from the paper. The discriminator is trained almost exclusively with one single example of what perfection looks like.
Just one.
Just one positive example. A vector that's all zeros. Zero error for every objective.
Wait, how does that work? How can it learn what's good or bad from just seeing perfect one time? That sounds counterintuitive, like learning music by only hearing one perfect note.
It does sound counterintuitive, but that's one of the key findings. It sees that single instance of absolute perfection, the zero vector. Then it's fed countless examples of imperfection, the actual error vectors the character generates as it tries to learn the movement.
Ah, okay.
By constantly comparing these imperfect attempts against that single ideal state, it learns to recognize patterns. It learns what combinations of errors are better or worse, essentially figuring out how to balance the trade-offs between different objectives to get closer to that all-zero ideal.
So the character, the learner, is trying to generate error reports that fool the discriminator into thinking it's hit zero error everywhere.
Exactly. It's this adversarial setup. The motion generator tries to produce differential vectors that look like the zero vector. The discriminator tries to correctly spot that they aren't the zero vector, that there's still some error.
Yeah.
This constant push and pull forces the motion generator to get better and better, minimizing errors across all objectives, because the discriminator learns dynamically which errors are most salient or problematic at any given stage.
That is a really neat way to sidestep the manual weight tuning. Okay, but the paper mentions a potential problem, degeneracy, and using a gradient penalty to fix it. What's that about?
Yeah, that's important. In these adversarial setups, sometimes the discriminator can become, let's say, too good or too simplistic. It might learn to just output a hard yes, only for the absolute perfect zero vector, and a hard no for everything else.
Like a really harsh critic, perfect or fail, nothing in between.
Exactly. It becomes like a delta function, very sharp, very uninformative. It doesn't give the motion generator any useful feedback on how to improve if it's not perfect. There's no sense of getting warmer.
Okay, so it stops being helpful for learning.
Precisely. The gradient penalty is a regularization technique. It basically encourages the discriminator's output to change more smoothly and gradually as the input error vector changes slightly.
Ah, so it forces the critic to give more nuanced feedback, like partial credit.
That's a great way to put it. It stops the discriminator from having these super sharp cliffs in its judgment and ensures it provides a more useful signal, a gradient that the motion generator can follow to actually improve.
Makes sense. Okay, so how did they actually apply this ADD idea to get the characters to imitate specific movements?
So they plug ADD into a reinforcement learning setup. The character tries out movements, and instead of getting a reward based on a hand-coded function, its reward comes from the ADD discriminator.
Okay.
During training, they compare the character's current state, joint positions, velocities, etc., to the corresponding state in the reference human motion clip for that exact moment in time. The difference between the character state and the reference state forms that differential vector, the error report.
And that gets fed to the discriminator.
Right. That's a negative example. For the discriminator, it represents tracking error.
Huh.
The only positive example it sees is that conceptual perfect tracking, zero difference.
Got it. So the discriminator learns to spot any deviation from the reference motion.
Exactly. And then the output of the discriminator, how close it thinks the current error vector is to that ideal zero vector, becomes the reward signal used to train the character's movement policy. A higher output means you're closer to perfect tracking, encouraging those actions.
And this focus on tracking a specific clip frame by frame is what makes it different from older adversarial imitation learning methods.
Yes, that's a crucial distinction. Those earlier methods like AMP were often about matching the general statistics or style of a large dataset of motions. They learned, say, a plausible walking gait, but not necessarily this specific walk. ADD is laser-focused on precise replication of one target motion clip.
Which is what you need for certain tasks.
Exactly, like animating a specific choreographed dance move or accurately showing how an expert performs a physical task.
Okay, so when the discriminator is making these judgments, what information is it actually looking at? You mentioned the observation map.
Right, it's not just raw pixels or sensor data. They extract a specific set of features that are relevant to the motion. This includes things like the global position and rotation of the character's main body, or root.
Okay.
Then the positions of all the other joints, but importantly, relative to that root in its local coordinate frame. Also, the global rotations of the joints, the linear and angular velocity of the root, again in its local frame, and the velocities of the other joints, also localized.
Could you quickly explain local coordinate frame again? Just make it concrete.
Sure. Imagine the character itself has its own internal sense of forward, up, and sideways, based on how its torso is oriented. That's its local frame. Measuring joint positions and velocities relative to that frame makes the information less dependent on where the character is in the world or which way it's facing overall.
So it focuses on how the limbs are moving relative to the body.
Exactly. It simplifies the problem for the learning system.
Okay, got it. So the big question, did it work? What kind of results did they get with these characters?
Oh yeah, the results were pretty impressive. They tested it on 2 simulated characters, a standard humanoid and also a model of that Sony evil robot.
And the skills.
A really diverse range: running, jumping, backflips, crawling, getting up off the floor, spin kicks, climbing, and those parkour moves like vaulting and that double Kong jump we started with.
Yeah.
Honestly, you have to see the video they released. It really shows the fluidity.
How did it stack up against the established methods, like Deep Mimic or AMP?
That's where it gets really interesting. So
Yeah.
AMP, as expected, wasn't great at precise tracking because it's designed more for general style imitation. Makes sense.
Right.
Deep Mimic, which is designed for precise tracking using those manual rewards, did pretty well. Similar quality to ADD on many tasks based on metrics like position tracking error and joint velocity tracking error, basically how closely they followed the reference. But ADD achieved that quality without the painstaking manual reward engineering that Deep Mimic requires. And crucially, Deep Mimic failed on some of the really challenging motions.
Like the double Kong.
Exactly. On the double Kong, the Deep Mimic character often just couldn't clear it. It would stumble or fail the jump. ADD managed it successfully. Also, on a large dance motion dataset, Deep Mimic's results were apparently quite jittery, while ADD produced smoother animations.
So ADD seems more robust, maybe more versatile across different types of motion?
That's what it looks like. And the researchers really stressed the difficulty of tuning Deep Mimic. It has many parameters, and getting them right for one motion doesn't guarantee success on another. They did sensitivity tests showing performance could vary wildly depending on those settings. ADD, by automating the objective balancing, seems to avoid a lot of that manual hassle.
That's a huge practical advantage. Now, they didn't just stick to character animation, did they? They wanted to show ADD was more general.
That's right. They applied it to some standard RL benchmark tasks, too. One was the 2D walker, a simple 2-legged figure that needs to learn to run. They used a pretty simple differential vector for ADD, just based on errors in target height, torso angle, and forward speed. And ADD achieved performance comparable to a baseline method from the DeepMind control suite, which used a much more complex, carefully hand-tuned reward function.
Again, highlighting less manual effort for similar results.
Exactly. And they also tried it on a simulated Unitree G1 quadruped like a robot dog.
Yeah. What was the task there?
Getting it to walk and follow specific velocity commands. Interestingly, the gait learned by ADD looked more natural, higher foot clearance, longer strides compared to the gait learned with a traditional manual reward function.
More natural, but maybe less precise.
It was slightly less precise at hitting the exact target velocities, yes, but it showed better torso stability and smoother control overall, which, for a real robot, might actually be preferable sometimes.
So it shows ADD isn't just for animation. It's a potentially useful approach for general multi-objective control problems.
That seems to be the implication, yeah.
Okay, and they also did an ablation study to figure out which bits of ADD were essential.
Right. They focus on that gradient penalty we talked about earlier, the thing that stops the discriminator becoming too simplistic.
The partial credit mechanism?
Kind of, yeah. They tried applying it in different ways. Not at all. Only to the negative samples, the actual error vectors. Only to the single positive sample, the ideal zero vector. Or to both.
And what was the key?
The key finding was that applying the gradient penalty specifically to the negative samples, the examples of imperfect tracking, was absolutely crucial. Without that, performance dropped off significantly.
So making sure the discriminator gives useful feedback on the errors is critical.
Exactly. It really highlights that the penalty isn't just a minor tweak, it's fundamental to making ADD work effectively by shaping how the discriminator learns.
Got it. Now, no research is perfect. Did they mention any limitations or future directions?
They did. They acknowledged that for some really fast, dynamic motions, like continuous rolling, ADD can sometimes get stuck in suboptimal solutions. Apparently, traditional methods often use extra heuristics or tricks to avoid this, which ADD doesn't currently have.
Okay, so room for improvement there.
Definitely. But they also pointed to a really exciting future direction, using ADD to train a single generalist controller. Imagine feeding it a huge data set of diverse motions, running, jumping, dancing, climbing, and having ADD help train one policy that can perform all of them, without needing separate hand-tuned rewards for each skill.
Wow, that would be a massive step forward for creating versatile virtual agents or robots.
Huge. And they also suggested exploring ADD for other multi-objective problems outside of motion, like in computer vision or maybe natural language processing, where you also have competing goals to balance.
Fascinating potential. Okay, so let's try and wrap this up. What are the main takeaways from this deep dive into ADD?
Well, I think the core message is that ADD provides a really compelling new tool for multi-objective optimization. Particularly for realistic character animation, it offers a way to achieve high-fidelity motion imitation by automatically learning how to balance different goals, which cuts down significantly on the manual tuning needed with older methods.
Yeah, and for me, the real aha moment is still that core idea of the discriminator learning from effectively just one example of perfection. Using that single ideal state to guide this complex learning process, it feels quite profound, actually, and maybe applicable much more widely.
I agree. And for you, the learner, hopefully this gives you a sense of how cutting-edge research is finding ways to automate complexity. It's a shortcut, in a way, to achieving sophisticated results by letting the system figure out the tricky balancing act itself.
So maybe a final thought for everyone listening. Think about areas in your own life or work where you're juggling competing priorities. Could you define an ideal outcome, your equivalent of that zero error vector? And could you think about the deviations from that ideal, your differential vectors? Maybe framing problems that way, even just mentally, could spark new ideas for finding better solutions.
That's a great challenge. And if you want to dig deeper into this specific research, definitely check out the original paper by Zhang and colleagues from 2025, and especially watch that supplementary video. Seeing the results in action is pretty convincing.
Fantastic. Well, thanks for breaking that down for us. Really interesting stuff.
My pleasure.
And thank you for joining us on this deep dive. We'll catch you on the next one.